This is the second part of the lecture on magnetotellurics, MT. So we will discuss how to use the data which is acquired on the field. Remember that at one station we basically measure the electrical field components, so the surface electric field, E, Y, Ex, and the free components of the magnetic field, Bx, By, and Bz. What can we do with these measurements? So we need to first recall what are the governing equations for electromagnetism. So that's from last week's lecture. We have Faraday's law. The curl of E is equal minus dB dt. Ampere's law, the curl of B is equal to mu 0 J. And Ohm's law, E is equal rho J. Right here I have expanded this equation such that you see all the components, such that these ones are those which are measured here, and these ones are those which are measured there. So we now assume a plane wave. So the variations in X and Y will be neglected. All the partial derivatives with regard to X and Y cancel out. So basically, we look at this equation here, and we look at this equation there. So this equation here, if the partial derivatives with regard to x vanishes, simplifies to dEx dz is equal minus dB dt. And for the x component of Ampere's law, dBz dy vanishes and minus dBy dz remains. And this is equal to mu 0 Jx. And then we have Jx is equal Ex divided by rho. So that's after making a plane wave assumption. These are the three equations simplified. What can we do with this? Let's combine Ampere's law with Ohm's law. So we will basically combine these two equations, and Jx will disappear from here and will be substituted by this part here. So we have dBy dz minus sign is equal mu 0 over rho times Ex. And now we take a derivative along the z-axis, and we assume that the resistivity is constant. So we make the homogeneous subsurface approximation. So if we take the derivative of this equation with regard to z, we end up with a second derivative of By with regard to z on that side, and the first derivative of Ex with regard to z. Rho is outside of the derivative because it's assumed to be constant. Now, let's combine Faraday's law with this second order equation, and we end up with d second By dz 2 is equal mu 0 over rho dBy dt coming from Faraday's law. And now let's use an ansatz for a wave. So an ansatz is basically an exponential solution that are taken of this form because exponential functions are easy to derive and easy to integrate. So now we assume a specific form for the magnetic field component y. It has an amplitude by0 and an exponential term I omega t. So I is the imaginary unit and omega is the angular frequency and t is time. So if we inject this, we can check first the derivative with regard to time of this. So the derivative of exponential e omega t is o e omega b0 exponential e omega t. So this simplifies to I omega by. That's the derivative of this. So we can inject this into this. So now we have the second derivative of by with regard to z is equal to mu0 over rho times I omega by. It's a differential equation. You have the second derivative of by on one side and by on the other side. This differential equation admits the general solution by is equal exponential minus I gamma z. You can check it. So if you insert by equal exponential minus I gamma z into this equation, you will obtain 0. Feel free to check this solution. So after inserting this solution into our previous equation, we end up with the following equality. We have I gamma by is equal mu0 over rho Ex. And what we're going to do here, we will be interested in monitoring the ratio of the components of electric field and magnetic field that we measure, this Ex, for example, and By. So we will divide Ex by By. So let's do this thing, and then we end up with I Ex over By is equal gamma rho divided by mu0. That's an imaginary number. So if you want to monitor its magnitude, we will take the module of it and we will square it for simplification purposes. So that's now what we obtain. The module of this is simply Ex over By to the power 2. And this is equal to gamma square rho square divided by mu0 square. So that's very important result. Because if we now insert this previous result, we will basically simplify this. So we have Ex divided by By to the power 2. It becomes rho omega divided by mu0. And this equation gives you the ratio of two components of the electric field. It has the resistivity, the angular frequency, and the permeability. You can solve it for the resistivity rho, and one obtains this final result. So that's a very important one. The resistivity is the permeability divided by the frequency of the wave times the ratio of Ex divided by By to the power 2. So this means that if you know Ex and By that you measure on the field, this value is known, it's the permeability of the vacuum. And if you know something about the wave angular frequency, you can know, you can deduce the resistivity value. So that's, of course, for the case of a plane wave condition and a homogeneous subsurface. These assumptions are to be kept in mind. So now let's go back to the skin depth. This we briefly discussed in the first part of the lecture. So the skin depth corresponds to the depth Z, for which the surface value is reduced by a factor 1 over E. So 1 over E is 1 divided by 2.71828. It makes basically 0.37, 37% of the value. So since we went that far, we can now calculate the skin depth. So let's take By at Z equal delta, the skin depth. It should be equal to 1 over E times By evaluated at Z equals 0. So we can use this solution here. So B at Z equal delta is simply exponential minus gamma delta. On the right hand side, we have 1 over E times By at Z equals 0, makes 1 over E exponential 0, simply 1 over E. Then you take the log of 1 over E, minus gamma delta is equal log of 1 over E, and this is simply the log of 1 minus the log of E, and the log of E is 1. So it makes minus 1. There is a simple relationship now between the skin depth delta and the parameter gamma. So once again, we can reintroduce this previous result, gamma square equal mu0 omega divided by rho. We inject it into the definition of delta, and you end up with delta is equal to the square root of rho divided by mu0 omega. That's the skin depth, which was as defined in the first part of the lecture. So now we can go back to the exercise. In the exercise that you're going to have to do, I will provide you a recording. So in this recording, you will have 4 components, Bx, By, Ex, Ey, measured at one station in Sudan. And you will be basically asked to evaluate the skin depth and the resistivity. And for this, you can use the two formulas that were just derived in the previous slide. Now I show you a couple of applications of MT. So there are many applications of MT. And here is an application to a geothermal area in Iceland. So it's a resistivity imaging of the subsurface. So you see here on the scale of 4 kilometers. And the subsurface resistivity is also correlated with drill holes here. So you get to know the structure of the reservoir at depth. Another example here is using MT to find water in the subsurface. So you can find water in deserts using, that's an example of a prospection in an alluvium in Saudi Arabia. And that's the one of the first pictures I showed in the first part of the lecture. It's a study of the water cycle in a subduction zone. So this is MT imaging at a very large scale. So using a long wavelength. So you see here the scale of 120. large variation of resistivity that are interpreted to be related to the subduction zone. So you see a subduction zone going on here, and you have a volcanic arc, and of course you have fluid and partial melts interacting at depths, potentially causing variations in patterns of resistivity at depth. And that's the picture from the Cerro Buco volcano. That's work that was done at the University of Frankfurt in the previous years. And basically on this picture, you see a map of resistivity with depths and the different regions below the volcanic edifice may represent regions where the magma is being stored at depths. So, as a conclusion, MT is a method which is based on EM. It's a passive monitoring method, so all the sources are natural, and they can be used to map out the resistivity structure at depths. And one of the advantages of MT is that it's sensitive to a large range of depths, including mental scale. Thanks for your attention.